All right, welcome to lesson 5. We're going to be looking at connecting f prime, and f double prime, specifically the connections between the graphs of these different functions. So we have our original function f of x, which is this red graph here, our derivative, which is this blue dashed graph, and then finally the second derivative, which is this dotted line here. So some of these things are going to be reviewing concepts that we've already talked about up to this point, but kind of mostly focusing on the graphs. So a function is increasing when the slope of the function is positive, right? That's a pretty easy one, right? Something has a positive slope, that means that it is going up or increasing. So if you look at our original function here, you know, in this section between those 2 points, obviously the graph is increasing and has a positive slope. Similarly, a function can be said to be increasing when the derivative, right, f prime, is positive. And then on the graph, what does that look like? It is above the x-axis, above the x-axis. So let's take a look at these graphs here. So we can see that our original function here is increasing all the way up to this point. We'll just say right there, and all the way to the left. And you can see our derivative function is positive or up above the x-axis in that same um, interval, right? From negative infinity all the way up to this value, somewhere around 1.5, right? And then again, our function is increasing starting here and then going to infinity. And that is exactly the same point that our derivative starts being up above the x-axis or positive. All right, now moving on, a function is decreasing when the slope of the function is negative. So we can see our original function here is decreasing in between this point here and this point right here, around 1.5 to maybe 3.25. It's decreasing over that interval. And it's also said to be decreasing when f prime, the derivative, is negative or below the x-axis. When it's negative or below the x-axis. And you can see here, between these values right here, between 1.5 and maybe around 3.25, the derivative graph is below the x-axis. All of these values are negative, and that lines up exactly with the intervals where our graph is decreasing in between 1.5 and that 3 value, right? All right, moving forward, a function has a minimum or maximum relative extrema value when the slope of the tangent line for that function is 0 or horizontal, right? A 0 slope means that it is horizontal. And so we can see that here in a couple places on our original function. We can see that we would have a horizontal tangent line right up here at the top of this graph at its maximum, its relative maximum there, and then a horizontal tangent line right there at this relative minimum value. Okay. That also occurs when the derivative f prime is equal to 0, or undefined. That is another time that this can happen, is when our derivative is undefined. Changing sign from positive to negative, right? So if a derivative changes from positive to negative, that indicates that we have a maximum point. And if it changes from a negative to a positive, that indicates that we have a minimum point. And so we can kind of look back up here and see how this applies. So here, again, we have that relative maximum up here and relative minimum there. And those align with these zeros of our derivative, right? When the derivative equals 0 or crosses the x-axis. And in this first situation, our derivative changes from being positive to being negative. So it goes from increasing to decreasing, and so we get that maximum value up there. And then in this situation over here, the derivative goes from being negative below the x-axis to being positive above the x-axis. And we can see again, it goes from decreasing to increasing, causing us to have this relative minimum point there. We'll go ahead and get rid of that stuff. Okay. Adding to this, right, crosses the x-axis. Now, next thing we can talk about, this is more of a new concept for us here. A graph of the function is concave up. You can see that looks like this when f prime is increasing. So when the derivative is increasing, that is when a graph is concave up. So if you have a section where your derivative is going up, that means that the original function is concave up in that section. Or when f double prime, the second derivative, is positive. And hopefully that makes sense, right? The second derivative is the rate of change of the first derivative. So if the first derivative is increasing, that means the second derivative is positive because that's the rate of change of the first one, right? It's increasing, it's going up. And then a graph f of x is concave down when f prime, the first derivative, is decreasing, or when the second derivative, f double prime, is negative. And again, those kind of go along with one another because the second derivative is the rate of change of the first derivative. And so if the first derivative is decreasing going down, that means that it has a negative rate of change, meaning the second derivative would be negative. All right, so let's kind of look at this concave up, concave down idea with our graphs up here. So our graph is concave down in this region here, right? It's like a cup that's facing downward. That's kind of one way I like to think about it, concave. If we make this part into a cup, right, that's kind of like upside down. You couldn't fill water into that. So that is supposed to indicate that our second derivative is negative in that area, or that our first derivative is decreasing in that region. And so you can see if we look at our first derivative, it is going down in this region here where we have concave down. And the second derivative, right, it's negative in the same region that kind of aligns with this concave down area. That it is very negative, causing that concave down. And then similarly over here, we have a region of our graph, our original function, that is concave up, right? So it's sort of like a cup, and if you filled that with water, right, we could fill that up. So in that case, that means that in the same region, the first derivative is increasing, and you can see it is, right? It's going up in this region. So it's an increasing first derivative, which again is a sign of having it be concave up. And then again, in this same region, if we look at our second derivative, it's highly positive over here. Right, it's way up there above the x-axis, again, lining up with this same region. Now, however, there is a kind of a cutoff point, right? Right in here is where there is a transition between our concave down and our concave up. And that is something that we refer to as an inflection point, which is the next thing we're going to kind of look at here. So an inflection point. All right. So f of x has an inflection point when f prime of x has a horizontal tangent line, or changes from increasing to decreasing, or vice versa, right? It could also go the other direction. Right? It could go from increasing to decreasing, or it could also go from decreasing to increasing. Both of those situations would indicate an inflection point in our original function, f of x. Or the other thing is f double prime of x is 0. If our second derivative is 0, that indicates an inflection point, or that also aligns with where it crosses the x-axis. So inflection points occur, just a quick summary here, when our graph changes from a concave up to concave down, or concave down to concave up. and that is our inflection point in this case up here. And that's going to be indicated on the first derivative by having a horizontal tangent line, or where it changes from increasing to decreasing, or when the second derivative is 0 or crosses the x-axis. So again, let's take a peek back up at that original function all the way up there. Okay, we got a lot of stuff going on here. Let me see if I can kind of clean this up some. All right, so I said there is an inflection point here somewhere where our graph changes from having a positive slope to being concave up to concave down, or whichever direction it's going. And so we'll just say it's kind of right here, right? Because on this side we are concave down, and on this side we are concave up, and somewhere in here, right, this is where it's changing over. So this is our inflection point. And so that should line up with two things. One, where our second derivative is 0 or crosses the x-axis, so that's right there. Our second derivative graph is crossing the x-axis and lining up with that inflection point. Or when our first derivative has a horizontal tangent line. And again, you can see right here, it is lining up with that as well. It's at the same x value. Those are both indications that this is exactly where our point of inflection is. All right, I'm going to go ahead and stop right there. We'll do those practice problems in another video.